Okay, non-allocating future promise. Basically, this was an idea that Chandler in the corner there was working on at the end of last BoostCon. And like we went out for lunch or whatever, and Chandler's a bit of a nerd. He'll be coding at lunch, he'll be coding like all the time. And he was working on future promise, standard future promise in Clang, and he was trying to make it get rid of the allocator that's required there. And he was doing it one way, and I was like, ooh, that's a cool problem. Because I could picture the problem in my head. It's a small enough problem. And I've given talks here for a few years on lock-free and stuff like that, but I've been looking for a real problem instead of just the little fake problems that you do in talks, you know, a problem that'll fit on a slide or something like that. I wanted like a real live problem. And as soon as Chandler mentioned it, I was like, yes, that's the problem I've been looking for. Right? I'm gonna talk about that problem. And Chandler was going to do it one way, and I said, no, do it this way. And he said, no, that won't work. And I'm not sure. I'll have to find out if he managed to do it his way. I think his way doesn't work. But I might have misunderstood his way. So part of that important part there is that I saw this problem as a very interesting problem that is fun to think about and work on. It's not necessarily something you should do. I really don't know. I haven't compiled this code, actually. I haven't measured the code. I don't know if it's better, faster, you know, don't really know if it works. But to me, it's a nice example problem to look at. So I'm not suggesting you do this at home or at work. Do it at home all you want. I'm not suggesting you do it at work. So we're talking about standard feature, standard promise, which you guys probably went to a talk today already. So I'll try to run through the little intro really quick. This is standard feature. You can construct it and move to it and assign, but note that you actually can't copy them. You can only move. Move is good, copy no. And you can destroy them, and you know that's just a destructor, which is mostly harmless. And trust me, that is the funniest thing ever when I say that's mostly harmless. One, because I'm going to have to deal with it in the algorithm, but anyone who follows the standard, there's a huge discussion going on right now about what happens in the destructor of a future, and debates about how the standard got it wrong and it should work this way and everything. So that's just a little joke. It's mostly harmless. But I don't want to get into the reasonings why the standards committee is up in arms over what future does in its destructor. And there's a share thing, which I'm actually going to ignore, because I don't want to talk about shared futures. I just want to talk about the simple future. In a future, you can get a value out of the future, and what kind of this is like cut and paste out of the standard. In the standard, it says see below, and what it means is depending on what R is. If R is a reference, it's got certain slight semantics. R can be void, therefore it doesn't return anything. But basically, imagine it returns R. Like that's the normal case. So that's all we're worried about. We're not worried about returning references to things or anything like that. We just want to get a value out of the future. So does this class make sense? And you look at this class and you say, okay, great. I can construct one and move them around and get a value out. And I can just get values out. I can't put values in, which is kind of weird. But then it dawned on me. It's like, oh, I understand how this class works. You create your lottery number class, which maybe is a vector of numbers. And you create future lottery numbers. And then you get the lottery numbers from the future. And then you print them out. Awesome, right? It turns out it doesn't work that way, unfortunately. This actually, I think, throws right here because your future isn't valid and all this kind of things because you default constructed it.
So you tried. So you tried.
Yeah. I definitely wrote this and compiled it multiple times with different compilers, and tried. Here's a quiz question for you later. Which function in the standard does actually return numbers from the future? I'll leave that one for you to mull over. Just forget I said that because it doesn't make any sense, right? But I'll come back to it. So there's this other half, because I said at the beginning, future promise, right? There's the promise half of the equation. Same thing, it's movable but not copyable. Constructor, destructor, pretty normal stuff. And it's, ooh, you can get the future from it. So I was trying to construct a future from nothing, but I should have got the future from here, I guess, right? And you can set a value. And there's another one of these see below things. This see below is slightly different. not only do you have the case of, well, what if R is a reference and what if R is void, but you also have 3 different ways of getting your value into the thing. And I don't want to always worry about which of these 3 we're talking about. So I'm just going to replace all these 3 with like a star, meaning any one of those 3. Wait, maybe star is not the right thing to use there. So I'm actually going to just use R, which is not any of the ones that I had, but that's what we mean. It's just like we're trying to, and see, it's R in italics. It just means we're trying to set the value into the thing, right? And later on, I need the slides. I need my code to fit on the slide, so I'm going to try to keep it short syntax. Oh, and promise takes an allocator, which is somewhat good because this talk is about the allocator of promise in future, and so it's good to know that one exists. But I would like to get rid of that allocator, or Chandler would like to get rid of that allocator, and I thought, hey, cool. So in a nutshell, these are your 2 classes, getting rid of all the parts I don't care about. And now it makes complete sense how I'm going to profit. First, you create a promise. You say, I promise to put the values into the future, and then I guess I'll have to calculate the lottery numbers myself, and then I can get them out of the future, and then I can profit. And that code actually works if I knew how to write the calculate function. And the only problem with that code is that it's kind of, this is a lot more straightforward, right? Why put the value? Because here's the amazing part, though. It's like a wormhole between the future and the promise. You call set value, and then it comes out of you set value on the promise, and the value comes out of the future, right? It's magic. So the reason we want to use promise in future is what happens if this calculate lottery numbers function is really slow, which it probably will be because what magic is it doing to give me lottery numbers? So imagine we had some concurrently. Let's do the promise part concurrently and do other stuff on this side of the fence and split them off into 2 threads. And I was too lazy to do the proper threading stuff. I just concurrently. And if I'm making up new keywords in the language, the best thing to do is to reuse existing keywords. And imagine we had this keywording. It's like, while you're doing this, also do this. Right? So, but the idea being, let's split off the future and the promise onto their own threads. And so let's forget about looking at code for a minute and look at the diagram. So we have our promise we call get future. Bing, there we have our future. And then later on, then we send them off each on their own way on separate threads. And these threads are obviously not synchronized. They're not synchronized swimmers. One's longer than the other. No synchronization between these threads, really. And magically, at some point, we'll call set value, and that value will show up on the get side with some magic quantum tunneling or something between the 2. So how does this work? Well, maybe the promise has a pointer to the future. And when you constructed the promise, it just set the pointer to the future. And the value's there, and we just call set value. Simple, right? I guess the talk is over. That was all. So what's wrong with this code here? Any obvious? I purposely wrote this the most explicit way I could possibly write it. The biggest problem I want to point out is that how do you know this pointer is valid? Because we mentioned that future is not copyable, but it's movable. And the future, is Eric here? Eric's not here, is he? Too bad. So I have to make fun of Eric. Eric is the future. Eric, Mr. Proto. They're both nomads. They move around. Eric was a nomad for a number of years. And like Eric, the future likes to move around to new memory locations. So you can't just be, that memory location is not where the future is anymore because it moved off somewhere else.
Could have just been destroyed too, right?
Or it could have just went away completely. So this isn't going to work. And so what Eric did, I'm sure, was read the standard on future promise. And since he spent his nomadic time before C++ 11 was out, he probably read the standard in the future somehow. But the standard talks about this thing, shared state. When you read through the future promise portion of the standard, it keeps talking about shared state, shared state. And basically what it is, and what Eric did, was set up a proxy address. So Eric could be out coding in Thailand, but if you want to send him mail, real mail, not email, but real snail mail, you send it to an address in San Francisco or somewhere, and then he'll get it later, right? And he just had this. So I think the government thought he was still in U.S. at all times, but he was all over the world. Not Eric, some other guy. It's being recorded. So basically, this is what it looks like. This is, in a nutshell, standard feature promise. You have this shared state that is independent of the two things, because both of those guys can move all over the place, and they have probably a shared pointer, some reference counting pointer to the shared state. And when you want to set the value, you set the value over here, and when you want to get the value, you come over here and get it. And if the value is not ready yet, you wait for it. What is wait for? Someone should have asked me that. That was one of the ones someone should. Well, what's wait for? Wait is for keeping us on the earth. It keeps held down. It's like, no. Wait for is just, imagine it's probably got a mutex, a convar, and a flag, whether it's ready, whatever. It's just, I just packaged it up because it's not really that important for our part of the story. So there we go. There's a future promise as is. And the important part is, who allocated this? This was allocated by the promise. That's why promise takes an allocator, because if promise by default will just allocate that with new. But if you want to use, some people are like, don't allocate anything without me being in charge of it. You can pass your own allocator, and it'll use your allocator to allocate that thing. So our goal is to get rid of this thing, because we don't like having to require an allocator and require allocation. So how are we going to do this? So let's just, instead of having this, let's see. Well, okay, right. One way of doing this, we could have maybe a pool of these things, right? And then, we could recycle them and stuff like that. But it would be actually hard, because do we have a pool for every type R, or do we have one pool for all these things? And these are all different sizes then, so we'd actually have to have a big block of memory that we'd have to pull things, and we would write an allocator, right? So that's what we were trying to avoid. We end up writing one. So we don't want to do it that way. So instead, let's kind of clean up this, get rid of the pointers, because we want to get rid of them, and just clear up my slides a little bit there. Any idea where we might want to put this if it's not going to be living in here?
In the future?
In the future. Oh, look, the future's got nothing in it right now. It's a nice big blank space. Yes, in the future is maybe where we want to put these things. And then we go back to the magic tunneling. And what are we going to use? What are we going to put here? Like, maybe we just put a mutex here. So I don't know how we're going to get at this mutex yet, but let's put a mutex there. And so at least now it's always the same size. It's not, shared states aren't all different sizes. It's they're all the same size. And before you ever move, or before you set the value, before you do anything, grab the mutex and be careful before you do anything, right? Of course, it's still shared state, and these guys would have to know where that mutex is. But let's say we do this, and I think this is roughly what the road Chandler was going down. Let's have a pool of mutexes, right? Just a few of them. And when the promise is first created, it will assign itself an ID that it can look up into this table, and the future has the same ID. So whenever they need a mutex, they come here and get a mutex that they can use. And then it's very simple. Okay, set the value, lock the mutex, do your stuff, unlock. Simple, right? And when you move, grab the mutex, do your move. Basically, we're imagining that each side has a pointer to the other side, so that when you move, you tell the other guy, hey, I moved over here. But you do with a lock, everyone's happy. And so that's kind of this idea here. But the one thing you have to remember is this is a fixed size pool. We don't want to be allocating in this pool. We're trying to avoid allocation. So you might only have 4 or 8 or some number right from the start of your program for the whole life of the program. You only have so many mutexes to use, and you have lots of futures and promises pairs. So what's going to happen is they're going to end up using the same mutex. These 3 might all be using that mutex, and these guys using that one. But for the most part, they hardly ever need the mutex, right? It's only when they move. It's only when they set the value, which is not a big deal. So is it a big deal that this future can't do anything if that future is doing something? It's like, there's probably not a lot of contention. Maybe that's not a problem. So let's imagine, in fact, that we've got 3 future promises pairs that are working on the same mutex, and we do this. Is there any problem with this? One of my biggest rules when doing locking code is if you hold a lock, don't call unknown code. Why don't you want to call unknown code when you have a lock? Deadlock, yes. Because that unknown code, well, you don't know what it's doing. It might go off and grab another lock and end up with this, somehow you might end up in a deadlock situation. So the question is, where is there unknown code in this diagram? Well, there's obviously unknown code here because I haven't shown it to you. But let's pretend that this unknown code doesn't do anything bad. Trust me on that. There's the WTF, obviously stands for wait for. The wait for, you set it to ready. That's probably got a mutex, and it signals the convar and everything like that. So, there is another mutex going on there, but that's a dead-end street. It's not going to cause a deadlock because it's kind of like a leaf node ending. So you can go into the ready and come back out. So where in the world is there unknown code? It looks like all the code is known. Oh, the copy constructor. Yes. What's this line of code doing? This line of code is moving or copying R. And what does that do? We have no idea. We don't know what R is doing. In particular, imagine R has 2 more futures inside of it. Kind of odd, but maybe you're some process that does some work and then splits it off to do more work and hands you back a partial result, or who knows what. People do weird things. We don't know what R is doing. If R just grabs a lock, that's not a big deal. But if R grabs another lock that's in a future promise, then it'll come back into this pool, and you're going to end up deadlocking where you have no idea where the locks are. You're just deadlocking inside this unknown. You don't even know there's mutexes involved, right? So that's kind of dangerous, and that's where I think that's roughly what Chandler was going down the road, and I quite imagine there's ways of fixing this problem. I mean, one easy fix is say, well, we mostly won't allocate, but sometimes we'll have to allocate or whatever, right? But to me, that was like, okay, that's not the way I want to do it. Partially, it's a dead end because I'm not sure how to solve it. Partially, it's just not the first way I wanted to solve it. Anyhow, I wanted to go back to let's say we've got a pointer to each other, and it's very simple. We'll just do very carefully set these things. Right? So we do know that we're going to set the value, and we're going to have pointers to each other that we're probably going to have to keep up to date. When we move, we'll tell the other guy that we're moving. And I've got big yellow here, right? We don't know that these pointers are valid, so we can't really be reading those pointers right now. How are we going to deal with this? So let's say, as a first try, we put an atomic int in our promise, and we set the state of the promise to say, hey, I'm moving. The promise puts up its hand. It says, I'm moving, right? That doesn't really help much yet, but let's say the future says I'm moving. The promise says, okay, I'll watch out for that. I'll watch, and if you're moving, I'm not going to do anything, right? Any obvious problems with that? So the biggest thing I'm just trying to say, sure, this is still unsafe. This is unsafe. Is this thing up there safe or safer or, right? And, that is the question. So what happens when this guy came in first, looked here and said, no, the future isn't doing anything, so I'm going to come down here, and then the future comes in and sets its state. Well, it's too late. I've already started. I'm going to mess around with this pointer. You're going to look at this pointer. You're going to get in a bad state. That's no good, right? So we can't have that. So it's kind of like the feel of it is good. It's like we tried to do something where it's like I won't do anything if you're doing something. So it feels a little safer, but there's still a problem, right? And safe or safe not. There is no safer in threaded programming. It either is always safe or it's not safe, right? So, okay, let's just throw some more code at it, basically. Let's do the same thing on this side. Say, well, if I'm moving, I will let you know that I'm moving. And if you're moving, you let me know, and I'll watch for you, and you watch for me. So, just stare at that for a while. One thing we're trying to do is we still have, well, no, I won't even go there yet. Let's see what my next slide is. That's what I'm going to do. we still have the same problem that this guy can fly into here, and that guy's up there, but now he'll stop, right? He won't get anywhere because I've set my state, he can't get past it, right? He'll get stuck on that loop. So what is the problem with this code? But where does the race, what race, what problem, what real race problem? And assume these are atomic, so we got sequential consistency where needed and stuff like that.
They both start moving at the same time.
I'm moving, yeah, me too. Oh, I'll wait for you. Yeah, I'll wait for you, right? They can both be stuck in this loop here, right? So, okay, that doesn't quite work. Let's say I will, well, basically we're going to still have that same problem, but let's just see if we can get rid of one problem here. Maybe I missed a case there. It doesn't matter. Let's say we get this far. This guy comes in, nothing's going on. It sets his state, sets the other guy's state, and the other guy hadn't done anything, so it successfully sets the other guy's state. This guy did race in at the same time, but now he has to stop. And one of the questions is, what was my question here, actually? The biggest question is, are the pointers safe? Can I read this pointer? And can I read that pointer? Like, this guy is about to read that pointer. Can he? Right? Or is that pointer is about to be changed? Right? So it looks unsafe. But actually, look at these two lines of code, this state of the program. This isn't possible to be in this state. This guy only got past the first step if he set himself to be moving. If he said, I'm moving, this guy can't say, no, I'm moving. This is like, you set yourself to move, you set the other guy to other guy moving, right? O move. One guy says move. If I'm moving, I set the other guy to O move, right? They both try to do the same thing. Once you set your state to move, the other guy can't change your state to O move. So if I get this far, this guy can never get past here, right? Which means when I read this pointer, no one's changing it on me. So I think my next slide is, I claim that these two pointers are now safe. And these two pointers are safe. That's kind of important. I also claim we still have a deadlock when they both race through at the same time. We'll still get stuck. We can both still be stuck here. But no one will get past here. Well, if someone gets past here, the other guy won't get past the first statement. He will never get to the point of reading a variable because he can't set his own state if the other guy's already passed him. So stare at that. Think of all the possibilities. This is what lock-free is all about. And convince yourself that that is true. Because we need to be able to read the other guy, the pointer safely. But we still have this problem where, hey, I'm moving, yeah, I'm moving, and we're going to work hard to set the other guy's state, but we're locked again, right? We can lock, but we don't have a pointer problem at least. So let's fix the pointer problem. How are we going to do that? Basically, I say, I'm moving. I go over, look at what the other guy's doing. And I say, oh, you're moving too. I say, okay, forget it. I'm not going to move then. I'll back off. And I swear in every slide I ever do at BoostCon, I end up writing a go-to. I don't know why. I don't write them any other time. So what do we got going on here? One guy comes in and says, I'm moving. Maybe the other guy does the same thing. Then I check what the other guy's up to. If he is moving, I'll go, okay, whoa. Set my state back to 0. Maybe I'm just throwing in pauses here so you're not looping. Who knows what pause does, but sleep or whatever. Something to make sure you give up. If you just spin, that kind of works. But if you happen to be on a good old machine that only has one processor and you decide to spin and you happen to be the thread with the highest priority, that other thread's never going to go anywhere and you're going to spin forever. So that's the priority inversion problems. So let's pretend there's some kind of slight pause where you give up your time slice or whatever needs to be done. So if I start to do something and the other guy's also doing something, I will back up set my state back to 0, hop back up to the beginning and try again. And other guy does the same thing. And exact same code, but now side by side because it's getting kind of big. And the fun of lock-free programming is just all you have to do is look at every possible state of the program, compared, cross product with every possible state of the other thread. And the best part about this problem is realize there's only 2 threads, right? The way future promise works, they happen on other threads, but I can't use this future on 5 threads. If I'm going to do that, I need to lock it separately, right? This feature is only being used from 1 thread. This promise is only being used from 1 other thread. So luckily, we only have 2 threads. In a lot of lock-free problems, it's all the possible states of all the possible threads. So this is nice and simple, right? So start imagining, okay, if I'm here and he's there, is that good? Are we okay with that? And in particular, if I'm down here, I say that guy is up there, and he can't get any farther. That's sort of what I was. It's sort of that same. Before we were deadlocked, but we couldn't get past it. So if I manage to get through here, he can't get past there. How do we prove that to ourselves? Basically, I came in and I set move to myself. I set the other guy to move. And I managed to get down here. I am here. He comes in. So one of the biggest things you have to notice, we're using CAS, compare exchange. If I didn't mention, that's what CAS is. We're using compare exchange in a lot of places because once I set state to MV, it's not changing, right? Because the only way you change is if it's 0. Once I set it to something, it's going to stay that thing until I set it. That guy never sets it to anything else. He tries to set it to OMV, but he never sets it back to 0. I'll set it back to 0 myself, but he only sets it to anything if it's already 0, and vice versa. And most of our code is like that. So if I manage to set my state to MV, set his state to OMV, he can't go anywhere. He is stuck up there. If he somehow got down here, it's not possible. That is my claim. He must be up there. And I thought I had more. Okay, so we didn't look at every single possible state of the thing. We just said this is the important state, and this is the key to everything. So feel free to stare at this all day long. Convince yourself. There's other locks that are kind of like this, Peterson locks and stuff, where the 2 sides kind of compare against each other to get into this state where only one can pass. It's not that crazy of an idea. Usually you're not using pointers to the other guy. It's usually just global memory or something. The basic idea of the algorithm is ask before you do anything. Set your own state first, right? Because you can't set the other guy's state. You don't know if it's valid. First thing you need to do is set your own state. Once you've set the flag of your own state, you know that guy's not going away because you put your hand up. Ask before you do anything, and don't leave before saying goodbye. So I put my hand up. The other guy is not going to leave until he tells me. And once my flag is up, he can't tell me. So he's not going anywhere. That's the key to making this work. So it's a very Canadian algorithm. So there's basically the algorithm again.
Does move self-set state back to 0?
That is a good question. You're too many slides ahead. The question being, who sets state back to 0? Imagine we clean up at the end. It didn't fit on the slide. So same code, but I'm going to crunch it up a little bit so I can fit some more stuff on. Yes?
You don't have to change the state back because you're moving to a different object.
Yeah, but
Repeat.
it better have the right state then.
Yes,
So
it needs to have the right state.
we'll think about that later too, because that gets tricky. So I claim this is all safe, but it's still it's safe in the sense that the other guy's not going to move. My pointer's not going to become invalid. But normally, when you dereference a pointer, what's the first thing you consider that might be unsafe about dereferencing a pointer? It might be null. So I've taken care of the hard problem, but there's still the simple problem of your pointers could be null. So simple solution, let's just check that first before we get into our state. No problem there. And that looks good. So anytime I do an if pointer, I get paranoid that the pointer can change on me, right? So I'm tempted to go through the whole thing in my head again, that pointer's not, and not only that pointer, but we have that problem everywhere, right? Every time you dereference a pointer, it could change on you between those two instructions. So I stop and get paranoid and go, okay, wait a second. Are you sure this is still okay? And I still have this claim of, this is the only guy who's going to change the pointer, right? Like if we're worried about that if statement over there, this is where that pointer gets changed, right? You're not worried about changing it yourself. You're worried about someone else changing it. And like I said, that can't happen. We can't be inside that, just after that if, when this guy's changing things. So we'll never have to worry about after the if, the FU isn't changing. Yes?
That's the only place it gets changed for a move. It can't
Yes.
change for other reasons, though.
Maybe. Oh, it only gets changed here for a move. Does it get changed other places? Currently, this is all we have. It's all the code we've written. So it's the only place it changes. So that looks good. I feel okay now. I just had to check my paranoia. But obviously, hey, I bet you there's other problems here. And like someone mentioned, well, shouldn't you clean up after? And here's the interesting thing. We've got two sides to clean up, right? I've set my state to I'm moving. I told the other guy, hey, I'm moving. And I have to set his state back to 0 and I have to set my state back to 0. Which should I do first? So not knowing which to do first, I wrote one like this, the other like that, right? And let's figure out which one is the right way to do it. What should the order of these two things be? So let's say this side first. Let's see if this can go first. We come down here, we've done all our work, and we want to set things back to normal. We know that guy's stuck up there at best. He's either not in the code at all or he's stuck here in that loop. We're down here. We set the state to 0, what happens? That guy pops out, right? He can go all the way down to here, but I claim he can't get past this. Because we've set his state to 0, but we haven't changed our state. So he can't get past this second if here. He can't set our state to anything. So all he'll do, gets out of his loop, comes down here, gets a false, goes back up and retries, sets his state, comes in here, gets a false, goes, now he's just in a slightly bigger loop, and he's still stuck. And then, what? I have an arrow. What does the arrow mean? The arrow is, part of the arrow is it still, we've gone farther. Is it safe to read the pointer now? We just asked you that question a second ago, but a second ago, we were stuck up there. Now we've gotten farther. Are these pointers still safe? Anyone? Flip a coin. Pointers are safe because he didn't move. When we were here, he was stuck up there. We've already set his pointer for him. Then we move down. Then he wakes up and he reads his pointer. The pointer's been long set. As long as we're using atomics properly with acquire release semantics, I haven't put all the memory orderings in here. But if we're just doing, assuming everything that needs to be atomic is atomic, that pointer is safe because it's been long set. Everybody's happy. That's OK. So then we set our state to 0. We're done. What's he do? He can come down out here, read his pointer, do his stuff. Well, basically, he can do whatever he wants because we're done. We're in no state at all, right? It's like he started from scratch. So yes, we can do it in this order, which is good to know.
PR was null in your conditional abide.
Yeah, I should check that pointer. Now, if this was null, the question was, what happens if this is null? If this was null, I have a lot less problems because I don't have that side of the code anymore. So in a sense, maybe the first thing I should do is check for null and don't do any threading magic at all. Just say, hey, there's no other thread to worry about.
Quick question.
Yep.
Does your move self 2 have to set the state of 2 to OMB?
Good job.
Because
Yes.
you. Okay.
Shh. I'll point at you when I want that question asked. So we said that that order works. Let's look at the other side of the thing. Let's do it in the other order. Say this guy came in first. Same thing. That guy's stuck up here, right? We know that. He sets his state to 0. What's this guy do over here?
He's still stuck.
Absolutely nothing. He's still stuck there. Wow, that was easy. He sets his state, the other guy's state, to wake up. He's completely done. And then this guy, he can come in and do whatever he wants because we're back to the no state case. So that works. It actually works a lot easier, right? Cool. So that's good. We can clean up ourselves. And there's a slight problem, though, of course. There's, always another problem left. And it was mentioned. And I've been really subtle about this to say, oh, I'm setting my state. I'm not setting my state there. That code is wrong. Because the whole time in your head you're picturing these two things, except for that guy over there. He's picturing these three things, because there's three things involved. I'm moving from this state to that, or this future to that future, or opposite, the other guy's moving, right? In a sense, there's 4 things involved, possibly, right? But one of them's blocked, so at most there's 3 things involved. So, go back to the, how many states do you have? Multiply it again by multiple objects. Wouldn't that be fun? Maybe I think we walk through this quickly. We come down here. We've got everything's, we've got we start out with this, and we want to move down to here. And we set the pointer, so now the other guy points down there, right? He's still stuck up there at the top of the thing, so he doesn't know what's going on. I come down to here. He wakes up, and he checks the state. What state does he check? Over here. He checks this state. Yes. What is this state? I don't know. It turns out I actually do know, but we'll get to that later. But we don't know what that state is. So maybe we better do this. Not set our old state, but set our new state. And how come there should be a 0 down there now? Maybe. Okay, I don't know. Set our new state and right. And then we can leave. Our new state is set. That guy will wake up. Everything will be happy, right? So we leave after here. What's the problem that's left? Yeah. What about this? This guy. He's stuck. He still thinks he's moving. If he ever gets reused again for something, it might cause problems. It's not very clean, right? So how about we clean that up a little bit? Oh, right, no, that was too early, sorry. Yes, we want to set this to 0. The question, I skipped, so back up 2 minutes in your head. Exception, roll back. That guy was looking at a state. We didn't know what that state was. And then I started talking about it being 0. We don't want it to be 0, do we? We need him to wait for a minute. We need this state to be MV. So, yeah. So, partially we know that we want to do this, but we want the state we're going to be move. We can set that right away, right at the beginning, right? It doesn't have to happen here. It doesn't have to happen in our kind of lock area. It can just, because basically the state we're going to, the future we're going to is ours, and nobody owns it. And is that true, that nobody owns that future that we're going to? Well, it might have a promise with it, right? But assume if we're moving into this new apartment that the other guy has already moved out. So in my real move constructor or move assignment, before I call this function, I will clear out the place I'm going to. Which means I call this code again with the null, so definitely we're going to have nulls. Two can be null, because I'm going to call it myself. So imagine that once we come into here, the place we're going to is nice and clean, right? So no one else owns it. There's no promise attached to it. We can set it now. In fact, we can set up everything now. We can set up the pointer that the promise it's going to point to. We can set up its value. Everything that we need to move, we can move right away.
So if you set PR before you do all of the cast.
Shh. So maybe PR we can't set yet. But we'll get to that. So the question, leaving that question aside, the question is, what about what's inside these prep and move to stuff? That's the rest of the struct, right, that we have to move. And remember, this is what our structs look like. And so far, promise is pretty darn small. It's got a state and a pointer. This guy, it's got a state and a pointer, and then he's got the value. And I didn't mention that before. I mean optional, like something. The value's not necessarily there yet because it hasn't been set yet. So it's a blob of space waiting for the value to go. So the future's a little bigger. The promise is pretty simple. It's got 4 bytes maybe in it or whatever. Or if you're really crazy, maybe you can set the atomic state as the low bits of the pointer of the future. So let's look at the promise, since it's the simple case, and make sure we get everything moved. We do the prep and the move self. So I claim there's nothing in that except for state and the pointer, and we've already taken care of state and pointer. We've set the state. We've set the pointer. We set the state. There's nothing else to do, right? There's no those little functions there don't actually exist. So what happens when we're in this state? We've set up our destination promise. We've got it all ready. And then this guy is here, and he's fine to be there because we haven't got anywhere yet. And like you mentioned, well, what happens if he changes the future pointer here? We're going to store the wrong one into the place we're going. So we can't actually do that FU set there. How about we do it way down here? All right? This is the safe zone. We can do stuff down here. This guy, if we're down there, this guy is up there. That's much safer to do, right? And that looks good. Let's maybe take a quick close look at that. Here we have, in this case, the future, or the promise is moving. We've got it all set up. We've got the destination, everyone's happy. And now we just have to set, that is not the right.
The arrows are messed up.
Yeah, my arrows are backwards. Darn. Well, ignore the arrows being wrong. The point being, that is right, though. What we're left with at this point is, we've successfully moved to here. This guy sees that we've moved there. Everything's happy. But we've got a pointer left over there, right? So if that other object gets used, that pointer is going to be odd. So we have to set our old pointer to null before we get out of here. And where would we might do that? It's tempting to do it up here because we only need to set it to null if it wasn't null. But we use it down here, so maybe it should be down here, right? So let's put it at the bottom. And as soon as I wrote that code, I'm like, ooh, wait a second. This tells me I'm done, right? That wakes up the other guy. But I'm not done yet. So I feel a little scared, right? When I get to here, where's this guy? He's anywhere. I woke him up. He can be doing anything right now. But what state are we in? This guy over here, once I get to this point, this guy is pointing down here. He doesn't know this thing exists anymore. That old guy is only owned by me. I can set him at the end. That's perfectly safe. Yay. Okay, and one last problem in that diagram. The MV and the old guy, right? I'm down here. Now the guy's left. He's still hanging out. He still says he's moving. So set his state to 0. Now I finish this. Everything looks nice and happy. Everyone's state is back to 0. We've successfully done the move. Oh yeah, but like we mentioned, we're not checking all our pointers. So let's check our pointers. That doesn't really cause any logic changes. And then we've got one last pointer down there. Let's move this stuff up to there. And what happens when you reorder your code in lock-free programming? yeah, you change the meaning, you go back to square one and think it all over again, right? But let's see what my next slide shows. It's the same reasoning. Well, actually, it's not the same reasoning. Remember how we said this order was fine or the other order was fine? I'm now choosing this order. I set the other guy to wake up, but I haven't set myself to wake up. This guy can get past the first while loop, but he's going to get stuck here, right? This thing is local to me. I can set this. I can do all this stuff, and when I get to this line of code is when he wakes up, because he's looking at, if he's here, he's looking at the new address. So that's when he wakes up, and then I set my old state, same as that. That's my old object. I can set it freely. So that is still safe. So I've checked all my pointers.
Don't you set null to
Set null.
in the final if?
Yeah, it should be. Yeah, you did. You said f 0 right there.
That? Is that good? That's great. This is what I want people to do is go, wait a second. I think I see something.
Oh, except then you copy it.
Oh,
Further down.
awesome. Yes. Yes, I set it to 0, so this is 0.
So that confuses me now.
Yeah. Okay, good. I knew there was a bug in here somewhere. I wrote all this yesterday. So I've had this idea in my head since last year, and I've been meaning to write it down for a year.
You'd be busy.
Yeah, and at some point I was like, okay, I'll give a talk on it, and then for sure I'll write it down. And the scariest part to me is that what I had in my head last year is different than what I did yesterday. So this is why I say this is just for fun. I don't guarantee, I really feel, stepping through it all, that I think this is correct, but I wrote it in one day. So, take it for what it's worth. So yeah, I guess the thing to do here would use a temporary, right? Good. There is a
Or
bug.
as you said, if it's null, then don't do any of the magic.
Yeah,
Do that early.
Yeah, that definitely could just do that. So let's phone home. Let's look at this side. So here's our old code on this side. The easiest thing to do is to cut and paste the code from that side, stick it over here, right? Leave our little prep in there and leave our move self because there's maybe things to do there. And basically, we've got our atomic state and our promise set because we had them correct. And it's exact same code over here, right? And now we just have to make sure we get the value and the wait for set properly. So imagine this. The question is, where can I move the value and where can I move the weight? I have to move them over. Can I do it up there? There's a big X there, so the answer is probably no. I can't do them up there because then I might be reading the value while the set code that we haven't seen yet, set value, is setting it. So I can't just be reading it up there in non-protected land. So I better not do any prep work up there. What did I just do? Oh, I just kind of, let's do it all here. Right, so the code kind of had to move around a little bit. There it is. There's all the moving of the new thing. And like I said, this weight object has a mutex and a convar and everything in it, but I don't need to move those because there's another one in my, it's like the fridge and stove. They're already there. And I claim no one's waiting on them. Only thing I have to move is the ready state, right? In fact, I'm the only one who waits on them. That guy will set the ready state sometime, and hopefully when he gets around to it, he'll be doing it in a protected way. So if I'm here, that guy's not changing the wait struct at all. And he's not messing with the value while I move it over. So how's that? Well, we have that same problem again, right? What's that code doing? And it's not so much that this code's going to go grab locks and everything. I don't know what this code is doing. It might take an hour to do this copy. Hopefully not an hour. But it could take a long time. while this thread is spinning in, just burning CPU. So that's probably not a good idea. So I claim that's not possible. That won't happen. Why won't that happen? Magic. This is supposed to be interactive. So if the value hasn't been set yet, we don't call the move constructor. This isn't optional or whatever. All it's going to move is the optional is not set. Hey, it's still not set, right? It does nothing if the value hasn't been set yet. So this won't be called if the future hasn't been set. If the future has been set, you haven't seen that code yet, but if the future has been set, guess what? The promise is left. Once it sets the value into the future, it can go, see you later, buddy. I don't need to talk to you ever again. So if this is set and I have to move the value over, this code isn't sitting over there because this code is gone, right?
Doesn't have to be gone.
It's going to have to be gone when we see the set value. Because you can only send the value across once, I hope.
But you get an exception if you do it multiple times.
Yeah, so that code can set a flag in itself to say, I've already sent the value along. Well, it doesn't have to set a flag. It can erase the future pointer, which is a flag to say, if you try to set the value, I'm going to throw an exception. Right? It's gone. So it will never be waiting on this other guy because it no longer is connected to the other guy. So that's good because I don't like waiting for an unknown amount of time in a crappy spin lock while stuff is going on. Right? And interestingly, this is a real case where I start thinking, there's a good chance the future's gone, or the promise is gone, because that's the whole point. The promise goes off and does a lot of work, and later on we read from the future. We might have to wait for the value, but hopefully it's done by the time we get there and the promise is long gone. So how about at the very top of my code, I check that there's no promise anymore, and I just do a simple move. I don't do any lock-free crazy stuff, and I just get the heck out of there. And partially because I'm trying to fit this all on one slide and because I write weird code sometimes when I'm tired. What does the easy move do, right? I need to copy the value and the wait state. And really all I need to copy, the value is either set or not. It might not be set because maybe this feature was created default constructed. So there's never been a promise. So the value's never been set. Or the value has been set and the promise is long gone. So if it's null, it's one of those two cases. All we have to move is the flag and maybe move the value if it's there, right? But once we get down farther into the code, down here, when we move, we're going to also have to clean up a little bit, right? And so crazy me to maintain that. I always need to move these things, and sometimes I need to do these things, so I pass a template parameter telling me how much work I have to do. It's a template parameter because these two ifs happen at compile time. So really, I've got 3 versions of this function for each particular case. Only because when I'm down here, I don't want to call move and then do the if on the 2 again. I'd rather only do it once because I'm really odd that way, right? So the only if is stuck inside there, but it also keeps it on one slide. So if I can, I get out right away. Otherwise, the code is the same. I move here, and if I'm moving down here, I make sure I do all the proper cleanup. And one little thing to think about, putting back the promise side just so we can refer to it. If I come down in here, I try to do something, no, the other guy's busy, so I come into this part, find the other guy being busy, and I say, oh, you must be doing something. I'll try again. There's a good chance that what the other guy's doing is setting my value, or leaving or something, right? So when I go to retry, why do I go here? Why don't I go all the way to the top and check if the guy left completely and maybe my value's set and I can get out early again? Well, I don't want to go all the way to the top because I've already set my 2 and did an if up here, and maybe that's an atomic assignment there, which is a little slower. So I don't want to do that one line over again. And obviously we're writing all this code because we want to be efficient, right? Like, we don't normally write this way. So, just stick it in here. And if you're wondering why I had 3 versions of this function, there was a 0, 1, and 2, that now you know. So this one has to reset the state, but it doesn't have to reset the pointer, which is the state and pointer. I couldn't fit the thing there, so that one's setting the state, it's not setting the pointer, and it just gets out right away. So, how's that? I think that's pretty good. Set value. Simple. We need to set the value, we need to set the state. So guess what? Let's take that same little magic code we had everywhere else. We stick the magic on either side and we put the thing in the middle. We got the same locking protection as always. And we got that same problem that this thing definitely is moving the value, and who knows how long that's going to take. And when it's doing that, what's the other side doing? He's there, the other guy is stuck up here in the loop again for an unknown amount of time. And whereas the other version I said it will never happen, this will happen, right? Wouldn't it be nice if instead of waiting in a loop like this, you could wait on a real object in this case, a real semaphore thing? If only we had something we could wait on, some wait thing that we do have a wait thing that we could wait on. So, and not only do we have a thing we can wait on, this guy's about to set it for us, right? So we'll wake up as soon as he sets that. But unfortunately, we're spinning in here. All we know is that we can't set our value. We don't know what that guy, we don't know if we're in move or we're in set value. Or do we? We do know, because this guy tells us what state he's in, and we can look and see what state he's in. So now, instead of just copping out when we see the other guy's busy, we're going to use a different version of the CAS that will tell us. CAS normally says, hey, if it's 0, set it to that. But you can also pass in the temporary there. You say that temporary, which is saying, is it 0? If not, the temporary will be updated to tell me what state it was in, right? So I'm reading the other guy's state in the failure case. It'll say you failed because the other guy is in the middle of a move or a set. And right, I'm reading my state. My state is set to the other guy is setting, right? Because he was nice enough to set my state for me so I can look and see what's going on. So I know the guy's setting, so I can wait till he's done. I'm not spinning, I'm waiting on a nice mutex or something. And then,
But you could set ready after you, or before you called wait.
yeah. So I'm assuming my smart mutex thingy takes care of that.
Should.
Signaling before you get there.
Should.
Yeah,
Just variables do.
yeah, convars do that, right? In any case,
If it's set, if it's notified before you wait, then you don't wake up. The wait blocks. You have to be waiting when you're notified, when the condition variable is notified.
and what if I put my convar thing in a loop that checks for ready, do the magic loop thing? Either, like,
No, you won't wake up. You'll be blocked because you won't get the notified.
right. That's a solvable problem, right? That's inside the WTF.
Another cast to solve that problem.
Hmm?
It involves another cast to solve that problem and remember the subatomic increment of depth.
Solvable problem, yes. So we will wake up, hopefully. We will copy the parts we need to copy, or set our new state, and we get out of there. And my claim is that I lost my temp there. That 0 is supposed to be a temp. If that 0 is a temp, I claim that this is nice and happy. And I also claim that I've gone off the screen. It's so much code you can't see it. So there's the code over there. Everyone believe me? Well, you better believe me because that's basically the last slide. So for your homework, what about set exception? Make that work. Set exception, same as set value, basically, right? Nothing to it. Valid, that's probably easy. Wait, maybe has a little trick to it, but it's hopefully easy. Swap. In the standard, promise has a swap member variable, future doesn't, but yet they're both swappable. I don't know why one has a member variable. How do you implement swap? Well, we implemented move, so swap is done. But I suspect you could make a better swap if you do it yourself. I claim that this thing can be created. You have to do that. Pause, who knows what that's doing a sleep or doing whatever you have to do. Ooh, exception safety. That can throw. And when that throws, if you just run out of my algorithms, I don't clean up the state and everything, so you're going to have to catch the exception, clean up the state properly, and throw. Those were all atomic operations wherever I thought they needed to be. I didn't really talk about it, but imagine that probably the pointers, definitely the state variable is atomic. I think the pointers need to be atomic in a small couple of places, especially when I check, is the pointer gone? Has to be atomic there. What memory ordering do we need? When I check the pointer being null, I probably only need an acquire. But that's a nice exercise. Go through and find, get that all right. You can just throw sequential consistency at everything. Shared feature, I just ignored. What do you, can we implement shared feature the same way? Or do you just go, no, it's a different thing. It really does have a shared object and screw that, blah, blah, blah. If shared feature does have to have shared state, does that mean promise needs an allocator? Or maybe future needs an allocator? Because you get the shared feature from the future, not from the promise. So that's odd. So if you're ever thinking of doing this, maybe you should measure whether this is beneficial at all. There's a few places in the code where, if someone was saying, well, maybe state is already 0 and you don't have to worry about setting it to 0. And there's actually a couple things you could probably throw out and still be correct. And maybe you should test it, but testing code like this doesn't usually find the problems. Prove correctness, that's easy to do. This is sort of in from easy to hard. Slight little problems. Technically, futures move and move assign and move constructor are no except. But in my case, I'm moving the value if it's already there, which could throw an exception. So, in fact, you can't do any of this just because it says no except. I guess you could swallow the exception or something. That would, that would make it no except, but it's not very nice. In the standard, it's no except because they're thinking the shared state's down here and you're just moving this future around. And, that'll never throw, right? Well, darn. And also, the effect of the move constructor is a future object that refers to the same state that was originally referred to. I don't have shared state that's being referred, so I don't know. Forget about the no except. I don't know if I pass or fail on this line, because I don't know what refers to means when you've got your state internally. Funny enough, the assign operator doesn't talk about refers to shared state. It just says, it's the contents of the other side, which is great because that's what I did. I moved the contents around. So, it's wishy-washy. Don't worry about the exact wording of the standard. And I think we're good. And that's the end. Here, let me go back to the code. Everybody happy? Big happy face? There was one question I forgot to ask everyone, and I didn't know where it came up, but I know where it came up. That's way far back. But when we were looking at all the possible states of things, way at the beginning. Not too many slides. This is just one of those. Right there. These I claim are all the places where state changes, right? That you have to check. Hey, something changed. What's the state of the other guy? 2 questions. That one's not a state change. Does that make sense why that faded one is not a state change? Because you didn't actually succeed in changing the state, right? So that's not a state change. This is a state change. And now I remember why that question mark was there. What's the value of state after you set it to 0? Pretty easy question, right? Come on. Maybe 0. It could be anything, right? As soon as you set it, the other guy could change it on you. That's why this state here is actually the same as the state at the top where you don't know what's going on anymore, right? But I don't know. I wish I had pointed that out at the beginning because that's what happens all the time in programming like this is like, you set something, what's it now? I don't know. I just said it. How am I supposed to know what it is? But that's the difference. I kind of did mention that's the difference between setting something like this with the raw set and setting something with a rule saying only set it if it's already 0. The other guys I know are going to stay their state until I want them to, you know. But that guy just changes, and then right after it changes, I don't know what it is anymore. So I don't know. I just personally, it's the one point I know I missed saying, so I went back to it. So Chandler, did you find a bug yet? This is your job, man.
So the funny thing, this is actually what I came up with first.
Yeah, you told me it wouldn't work.
And no, it was that it wasn't lock free, and it isn't lock free.
Right. It's spinning.
And the hope was that the pool of locks would be simpler and also not lock free. So like once we realized that we couldn't get anything that was like that it was going to have a lock in it, we were looking at simplifying it.
Right.
You also did miss one of the homework points, which was a little bit fun. Set value at thread exit.
Yeah. Yes. Notice how I just totally.
Repeat things.
Yeah.
It's not as bad
Sorry.
as you might expect it to be, though, because it only really matters if you care deeply about strict conforming C++11 implementations as relate to thread local variables and their structures.
Yeah.
And if you do care about that, that's great, because it also lets you solve the problem. You can move the promise and like the pair of the promise and the value into some container, some thread local container, like on the back of the thread local container. And have that container, when it's destroyed, walk through all the promises and values it's accumulated and set their values. And the same thing works for exceptions.
I'm going to attempt to repeat what he said for much shorter. The one thing was I didn't even mention, just tried to skip past as fast as I could, the function set value at thread exit. Because, if I was trying to write my own feature outside of, this wasn't standard feature, it was my feature, how am I supposed to, that is totally implementation specific stuff. I don't know how to mess with that, so I'm not going to go near there. Chandler knows how to handle that problem. The other thing he said, this is the algorithm he came up with, give or take, probably. Yeah. And the important part is this is not lock-free. It uses lock-free techniques, but lock-free, it doesn't have locks, but it has waits where some guy is spinning and waiting, so it's a crappy kind of lock. And the important part about that is, so this guy is waiting for this guy to finish. Let's say the scheduler tells that guy to stop for a while. This guy doesn't make any progress. He's stuck. The definition of lock-free is one of you is making progress. If the other guy gets stopped by the scheduler, I'll make progress. If you stop, I'll go. One of them is going. This, you have to wait for the other side, so it's not lock-free. I never claimed it to be lock-free. I claimed to get rid of the allocator. But yeah, you go through all this work, and that's why at the beginning I said could do, maybe not should do, because that's a lot of work for stuff. And maybe using a mutex, which I haven't, every time I ever do a talk on lock-free stuff, is my first slide is use locks. Don't do lock-free stuff. Ed, did you ever get anywhere with the mutex pool?
It gets really annoying with the recursive nature of things. You can
Yes.
do it, but you have to set up essentially, a deferral system so that you can handle the move. It's just a mess.
Yeah, I started.
It's less messy than this is if you think of it.
Yeah, I was in my head at least trying to go down. How do I deal with the pool of mutexes and yeah, I just backed away. So, yes.
Tony, I was wondering, have you given more thought to my original observation, which is the only sane way of doing this in a way that would be distinctly faster than the current version using SharedPoint, which is the one in the current implementation, is to use transactional memory, because of the ability to set multiple locks atomically with the transactional memory makes a lot of this complexity just vanish, and also, of course, get speed.
Yes. So the question being, what about using transactional memory for this? That would make life easier, I think. In fact, I think you could have the case where it gets back to being lock-free. Both sides run along and do stuff, and then at some point they see, whoa, we're inconsistent. Some guy rolls back, the other guy succeeds. And I obviously haven't thought about more than 5 seconds, but I think you can get a nice lock-free answer to that.
I think it's
Which-
one of the few areas where the transaction memory really makes the algorithm just
Go away.
benefits it.
Yeah.
It just transforms the situation.
Yeah, it would be it would be a simple algorithm. Just set your values and then, figure out the,
No, like, it's gonna, transactional memory is going to replace the careful cast-based state progression with a simple transaction rollback. But the thing is that you actually have to achieve your consistent state, and know that at some point, because you then rely on it, you'll reach into someone else's memory to change their state. You can't do that and roll that back correctly, right? Like, rolling that back doesn't actually roll it back efficiently.
right.
So like, I think the transactional memory is going to make this probably execute faster because it's going to take advantage of the cache concurrency protocols that will actually say like, yes, actually both your caches succeeded. You didn't wait for either of them.
Right.
Right? But you're still going to have this retry pattern.
Okay, I'm not going to be able to repeat what he said, but other than transactional memory will hopefully help, but not necessarily get rid of all the complexity. That's homework for next year. Anyone want to tackle that next year? I think that's the end of my slides. No questions? Thank you very much. Thanks for paying attention.